All right, hi, seventh grade or eighth graders today. Sorry. So today we're going over the Coriolis effect and rain shadow effect. Okay, so we have this sheet of paper here, and we have the northern hemisphere, right? So this lesson is all about perspective. So this one can kind of be tough to get because if you're only thinking about looking at this one way, right, you literally have to act like you're sitting on a satellite right now. In the satellite, we're hovering above the northern hemisphere, okay? And so you'll see that I got a couple arrows drawn right here that start here at the North Pole, and then they move down and around. And as I move down here, it moves down and to the right. As I move this, it moves down to the right. What these are wind patterns. If I let me go ahead and add another slide here. So if I go ahead and draw myself an whoa, way too big. If I go ahead and draw myself a globe, okay, and when I draw this globe here, I have my equator, which is the middle of the Earth, right? 0 degrees latitude. I know that around my equator here, I get the most intense sun energy. And so the sun bakes this equator here. So when we get this hot sun hitting the equator, we get this warm air. And warm air, we know, becomes less dense and it rises. Okay? And now from here, our hot air has two directions it can go. It hits this tropopause where our weather is, and it can either deflect one way or it can deflect the other way. And so it will do both. So in the northern hemisphere, this hot air from the equator rises, hits this troposphere, and then it will do this convection current where it gets super cold right here at the North Pole, and it will make its way downwards. And then this air then has to move along the surface of the Earth all the way back down here to the equator. This guy does the same thing, and then it gets cold, becomes too dense, and then drops back to the North Pole, and then it will move back here. And so what we have here is a very simplified version of a convection current, right? Hot material becomes less dense, rises, and then runs along the top where it gets cool. As it cools, it condenses and becomes more dense than the surrounding material. Thus, it sinks back to the Earth, okay? And so what we're looking at with those arrows is this surface wind right here. So this wind that we feel along the surface is what we're looking at when we go to here. So as that air drops down here on the North Pole, it begins to go to the south. But how come it doesn't go in a straight line? How come it's going in this curved line? Well, think about this. In which direction does our Earth rotate? All right, that's what this Coriolis effect is. It's due to the rotation of the Earth. Our Earth is rotating in a counterclockwise motion when we look here at the northern hemisphere. So as it goes that way, right, if we pretended that this Earth was actually rotating, I would try to draw a straight line from the North Pole down here to the equator. However, this guy is stationary, but once this guy starts moving, then we get the perception of that. And we get these curved lines that curve to the right like that, right? And this is if a wind tries to move straight, but we have the Earth's rotation we have to take into account. What goes good with this little explanation here is if you maybe go and pause this video right now and go to this guy right here. It says the Coriolis effect due to Earth's rotation. That's a great video to explain why that wind is acting the way it is. Okay, so let's get back to this. So we look at that, but then we also have our southern hemisphere. Our southern hemisphere, when I look at this, I was looking at the northern hemisphere and it was moving counterclockwise. Our southern hemisphere actually moves clockwise. And like I said, this is all about perspective now. And so if we have this ball, this northern hemisphere, right, and this guy is rotating to the east, we can see that it is, well, in the video it might be opposite. I don't know how those optics work. But anyways, the northern hemisphere does rotate to counterclockwise, and the southern hemisphere rotates clockwise. Okay, so with the clock, right? And so now if I'm trying to draw a straight line, whoa, my gosh, that's not a straight line. right? If I try to draw this line straight to the equator, that's if my line is not, my Earth's not moving, but it's rotating. So what actually this line would look like, because of the rotation of the Earth, again, what are we looking at? We're looking at this surface wind right here. So now, or we're looking now at this surface wind here at the South Pole moving this way. Okay, and so what's going on is this is actually deflecting this way. It's deflecting this way. And it's deflecting to the, well, that one was wrong. And it's deflecting to the left. It's deflecting to the left. Okay, sorry. I got a little confused with that. And so if you need help with this, go ahead and grab a sheet of paper, put them down on the table, put one, you might have to have somebody help you, or maybe you can just turn it with your hand. But start with your pencil in the middle of that paper and draw a straight line towards yourself. But as you're doing that, rotate the paper. And as you're rotating the paper, make sure your pencil's still drawing straight back to you, and you will get this curved line effect. And that's what's happening to our winds, is this Coriolis effect. Okay? And so what we need to do is we need to go back to this model. And so I kind of lied to you. This model right here, this model's too simple. Okay? The Earth in circumference is about 40,000 miles long. 40,000 miles long. That's really long ways. Okay? So if we look at the air moving from here to here, that's a quarter of the Earth. So a quarter of the Earth, that would be 10,000 miles, let's say, for rough figuring, right? So 10,000 miles, you think that this hot air would get up here and then for 10,000 miles travel to the North Pole and finally get cold enough where it sinks back to the Earth? No, it happens much sooner than that. And let's check out what actually happens. And so you should have a notebook out for this next part and draw this next part. So here are the notes that we took here in class about the Coriolis effect. It's going to look really complicated at first. It took me about 10-15 minutes to draw it all and explain everything. But I just left it up here. So I didn't have to redraw it with my mouse because I can't. It wouldn't be very nice at all. So anyways, as this thing's getting going, whoa, and we look at all of this, okay, and it looks super complicated. So let's start. And let's see if we can tear this thing apart and make it and chop it down into smaller parts. Okay, so the first thing that we start with, let's look at these air currents on the side here, this green, blue, and red. And so this is our simplified version this is oversimplified. What I'm looking at now is this. What I said was this guy rises, and then he travels 10,000 miles in the tropopause, and then finally gets too cold. Well, now we know that that's not actually what happens. We have 3 of these little cells that happen. Okay? See if I can bump the zoom up at all, 100 maybe. Okay, there we go. And so what happens is right here, the air does get baked and it gets hot and it does rise and it hits this tropopause and it either deflects to the north or it deflects to the south. Okay, once it gets to about 30 degrees north, it gets cool, it condenses, and it sinks back to the Earth and then runs along the Earth, and then it gets stuck in this convection cycle, right? Once it hits the surface of the Earth, it can go back south or it can go back north. So if you go north, then it warms up again. As it warms up, it hits the tropopause, then comes back south, and then repeats that process. Instead of going south, it can go back to the north, drop. Okay, and so that's how we get these 3 cells. And so what you have to imagine, too, is this is a 2D drawing of what the cells look like. If you can imagine like 3 tubes of air that wrap all the way around the Earth, right? If this is an orb, this would be a tube of convection current that would wrap all the way around the equator, between the equator and 30 degrees north. And this one would be a tube around all between 60 degrees north and 30 degrees north. And this one as well as up here. And so you'll see I have a couple notes on the side. So it says rising air makes clouds. So as this air, it gets heated, right? It's really hot air. What else is going on down here at the tropics? We know it rains a lot. Well, why does it rain a lot? Because we get a lot of rising hot air that's full of moisture. And when that moisture begins to rise, up in the cooler atmosphere. That cooler atmosphere causes these really, really energetic water vapor particles to now start clumping together and forming water droplets. These water droplets then form clouds. These clouds then are what give us rain. Okay, so we get all of our rainforests around the equator. This is why it's the tropics. And then over here, the rising air makes clouds. So then at about 60 degrees north, you're really not going to find a whole lot of dry places because there's rain that takes place. I'm not going to say a bunch of rain, not like enough for a rainforest, but there's really no dry areas if you look on the latitude 60 degrees north, and as well as down here, it's reflected on the southern portion as well, and on 60 degrees south, right, we have this rising air, so we'll get clouds here. So you're really not going to find any dry spots. So now let's look at all of these arrows that are in these different crazy ways. Well, again, we're looking at these surface air arrows. So if I start here at my Hadley cell, so this first cell is called a Hadley cell. It's because this guy named Hadley came up with the idea of it. And so if I am coming, so here we see over here that we have air coming from the tropopause, and it's making its way to the surface of the earth here at 30 degrees north. And if it decides to go south, it goes south, right? But it doesn't go actually in a straight line. As it begins to go south, it deflects to the right because of the Coriolis effect, right? Just like just like we showed here. So we know in the northern hemisphere, air, as you move to the south, if you travel, you will deflect to the right in the northern hemisphere. And so I'm traveling this way and I'm deflecting to the right. But then it's like, well, how does this change direction? Well, again, if this air is falling and now it's moving north, so I'm traveling north, right? This guy is deflecting to the right. So it says northern wind deflects to the right. Down here it says southern wind deflects to the left. So then again, if I'm up here in the northern hemisphere, this polar wind is dropping and it's traveling along the surface, it will, so you got to be going in that direction, right? So put your butt towards the pole and then head towards the equator, you will deflect or walk to the right. Okay, and then it's the opposite down here. If I go back to this other guy here, it's the opposite. In the southern hemisphere, if you walk from the southern pole and then I go up towards the equator, everything's going to deflect towards the left. So why is that? So again, this air over here at the Hadley cell, between these two cells, the air is dropping here at 30 degrees south. And then if it's traveling back to the equator, it's deflecting to the left. If it deflects to the north, again, I put my butt to the equator and then I walk towards the South Pole, it still deflects to the left. And then if I'm dropped off here at the South Pole and I start walking towards the equator, it will deflect towards the left. Okay, and that's a pretty short version of what happened in class today. The reason why this stuff happens is because different parts on the Earth are actually traveling at different speeds. And you're like, well, what the heck? What in the world? Here at the equator, it's about 40,000 miles in circumference, meaning all the way around, it's 40,000 miles. And so it travels that in 24 hours, right? And so if we wanted to figure out the speed of it, speed is just distance divided by time. So we know the time is 24 hours and our distance is 40,000 kilometers or 40,000 miles. Maybe it is 40,000 kilometers. I should probably figure that out. 40,000 miles or 40,000 kilometers. Anyways, the time stays the same, but as I go up to my latitude, 30 degrees north, well, since it's a sphere, this line right here, the circumference of this ball gets smaller. And so maybe instead of 40,000, it's 30,000. So now it's traveling less distance, but in the same amount of time. So you're going slower if you're standing here on 30 degrees north. If I go to 60 degrees north, it's even smaller circumference, right? And it's still traveling at 24 hours. So now we're going less distance in the same amount of time. So I'm still slowing down until I get all the way to my pole. And let's say that I'm standing 10 feet off the 90 degrees north. And now it takes me still 24 hours to travel 10 feet. That's a very, very slow time. Okay, so what's going to happen is if, again, this is kind of like a thought experiment. This is like a little bit of physics, forces, and motions. If I am, let's say I'm standing here on 30 degrees north, I'm traveling slower than anybody here on the equator. And so if I'm going down the road and I have this baseball in my hand and I'm playing catch with somebody else, let's say I'm in this big, big car. It's unimaginably big, right? It's big enough for me and somebody else to play pitch and catch. But in the exact opposite direction, so let's say to my right, we're traveling 60 miles an hour down the road, but I'm playing pitch and catch with somebody in this direction. So I'm traveling 60 miles an hour down the road. This car that I'm in is traveling 60 miles an hour down the road. Since I'm in the car that's traveling 60 miles an hour down the road, I'm also going 60 miles an hour. Anything that I'm holding, like this baseball in my hand, it's also going 60 miles an hour. And so if I end up throwing this ball to somebody else, that ball will still be going 60 miles an hour, and that person will catch it because they are also going 60 miles an hour. Now, here's where it gets a little tricky, is let's say now this bus gets split in half, and I'm left here at the 30 degrees north, and I'm going slower, and that other half of the bus now is at the equator, and it's going faster. And so if I'm throwing this baseball because I'm going slower and I try to throw it right across the street to this other bus that's going faster, I'm not going to hit the person because I'm going slower than them. So the ball will actually end up behind that bus, and that's why this deflects this way. The same way up here. If I'm at 30 degrees north, I'm going faster than somebody at 60 degrees north. So what's going to happen is, again, we're on this bus, and now the other half of the bus is on 60 degrees north. They're traveling slower than I am at 30 degrees north. And so when I go to throw the ball at them, instead of it going straight to them, this ball is going faster than they are, and so it will outrun them and land in front of these people. Okay? And I know that's kind of tough, but that video, if you keep watching it, it explains it a lot better. So there's that. So that's the Coriolis effect right there. And so the next thing we did is I went ahead and, so let's go and look at Google Earth. Let me go ahead and pause this for you guys. All right, so I'm back again. So let's look at Google Earth here. So if I actually look right here, we're looking at the United States. And where do we fall here in our Coriolis effect? The U.S., we actually fall between 60 and 30 degrees. We're right here. And so our winds, our weather comes from the west, and it travels to the east. And we know this, right? If you ever go outside and there's a storm coming, you're not going to look off towards Mount Sterling. You're going to look off towards Quincy, and our weather, Quincy gets the weather before we do, right? If somebody's in Quincy and they call you and they say, hey, it's just started raining, then you could probably bet on in about 30, 40 minutes, it's going to start raining here because that's where that weather comes from, because of this action right here. So let's check it out. And so if we end up looking at this, oh man, I can't draw on here like I could. So anyways, up here is about 60 degrees north. So Alaska's up here where we can't see it. So 60 degrees north runs just under Alaska. So way up here. And then 30 degrees north is right here at Mexico and runs through the tip of Florida. Okay, so between here and here, we can actually see down here. It gives me the latitude and longitude down here. So if I keep going, 30 degrees. All right, so here's 30 degrees north, about-ish. So this is 30 degrees north, and then up here is 60 degrees north. Oh, man, I'm good. Okay. So anyways, we get this wind traveling this way. So let's take a look here at this west coast. And so we get this air traveling this way. Well, we notice, oh man, this Washington, the state of Washington's nice and green. Portland's nice and green. Oregon, the Northern California, this all stuff's nice and green. But then we have these mountains here. And then we notice it starts getting really dry on this side of the mountains. Well, what's going on is we're getting this nice warm air that's going over the Pacific Ocean. So it's picking up a lot of moisture. And now it's hitting these mountains. And what's going on is as this wind hits these mountains, the mountains force the wind to start rising. Well, we know if it rises in altitude, what happens? Air begins to cool down. That water vapor that's in the air begins to cool down. Now it's starting to condense into clouds, and now we're getting this rain. We call it a rain shadow effect. And so now it's raining on the side that the wind is carrying it to. But then what happens is it's like a sponge. Is now that air, that moisturized air, is wringing itself out. It's raining. It's dropping all of that moisture. And by the time it gets to the top and then starts coming down the other side, it has no more moisture in it. and now it's a dry sponge. And what does a dry sponge do? A dry sponge soaks up any other moisture. And so now all of this moisture that's in this land here is now being picked up and is being picked up by this dry air mass and taken over here to the east side of the state, where we get that moisture that was picked up after it traveled over the mountains. Okay, we can also see this down here with with Brazil, Chile, Peru, with the Andes Mountains right here. So we have the Andes Mountains here. The equator is right here. Okay, so here's our equator running through Ecuador, through Brazil, right around here. Okay, and then, so we know that our air masses, if you're checking your notes out, your air masses coming from 30 degrees north to the equator are traveling in this direction. They go from here to here. Okay, so they're hitting this and they're dropping all of their moisture off. They're raining, stuff like that, and they're giving all of the rainforest, all of the moisture, and then all of the rain is coming, all of the wind is coming from here, and it's traveling this way across Brazil, hits the Andes Mountains, it rains, it drops this precipitation, and then all this precipitation runs in these creeks, streams, until it ends up here in the Amazon River, which is the largest river on the face of the earth. Okay, but then we look at this. So we get green, 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 and then it starts to change, and now this side is green, and this side's dry. So what's going on here? Well, this is, if I look, here's my 30 degrees. And so if we look, what happens between 30 degrees and 60 degrees down here? Well, let's go back to our notes. Between 30 degrees and 60 degrees, our wind is now traveling from here to here. So now this wind is picking up moisture here, and it's dropping it off on this side of the mountains, but now this side of the mountains is nice and dry. Okay, so now what your homework is, so that's just a little talk. What your homework is you're going to start talking about here. We have Las Vegas, and we have the Charleston Mountain. So here's Charleston Peak. So you're collecting data, you're graphing it, and you're comparing the graph from this small little mountain range here, and you're going to compare it to the Las Vegas Valley rainfall. And you're going to compare which one gets more rainfall and what's causing that. And again, if I keep my mouse here, here's where the mountain is. Okay, and so we know here's the mountain. We're getting, our wind is coming from here to here. It's going from left of my screen to the right of my screen. And so what's going on? Why is it doing that? So the only thing you have to do is graph that first page, it's got a data table on the first page. You'll flip it over, you'll see the graph. How about I just pull it up? Or actually, I have it on my smart notebook. So then you read about this. You're going to graph this guy. This is all one line. So you're going to graph this guy independently and make that like a solid line. What do I mean by graph that? Well, here's the graph. So you're going to graph it. It's like 14.45 is your first graph, and then the next one, and then you're going to connect the dots. It gives you a little chart over here, what your key should be. So you're going to have two lines that you're plotting. Here's your second line. This one's the Las Vegas region. And then questions 1 through 6 ask you about what's going on here in this graph. Okay. So if you have any questions, please let me know.